Hi there, this is Faye. Today I want to show you guys the project 2 about the 5 times 5-bit sign multiplication. So the goal is to write a Verilog module for the signed 5-bit binary numbers in 2's complement. So let's try it first. This is a D0 board, and when I choose 1 times 1, it's 1 here. And when I choose like 8 times 8, I can get 2 to the 6, which is 64. And if I choose two negative numbers, like negative 1 times negative 16 times negative 16, I got a positive number, which is 256. Okay, so I have two approaches to do this project. The first one is just the same as the book. If I get a 5-bit number here, when S is the sign bit is 1, it's a negative number, so I need to get the magnitude of the left 4-bit, which is here. Get opposite of it and add 1, and this is the magnitude. And when S equals to 0 is just a positive number, so the number itself is the magnitude. Then M and Q are the magnitude of the two numbers. Each has 4-bit. So I need to use Q0 to times each bit of M, and then Q1 times each bit of them. Then I get 4 rows of the numbers. Then I need to add the first row and second together, and then add the third row, and then add the fourth row. And this is the same as this diagram. I need to use AND gates and full adders. So for the code of it, it's like the M and Q are the magnitude of the two numbers. So I need to change to the the M and Q are the 5-bit numbers, and I need to change them to the unsigned numbers. So when the fourth, the most significant number is 1, I need to change it to an opposite number and add 1. Else it's just itself. Okay. And this is the main part of it. So this part here are for all the AND gates. I use Janver I and J to go through all of the AND gates. Then I can use an array 4 times 4 array X to store all the outputs from the AND gates. Then I use called the full adder function to add them together and assign P, the 8-bit number P, okay. So this code is just for 5 times 5. If I want to try n equals to 3, 4, 5, and 6, I need to get the general code for the full adders, which is here. I use Janver K and W, just like the AND gates for the full adders. And I go through all the full adders and find this is the general code for n equals to whatever it is. And then I need to connect P, the output, to the X, the array. And this is what I got to use module sim to get the simulation. And you can say here when M and Q equals to 0, 0, 0, 0, 0, 5-bit zeros, I can get the P, which is the output, to be 0, all zeros. And yeah, here when T goes further, can say that this is P here and M and Q here. Okay, that's just the approach 1. And for the approach 2, I use Wallen's tree, and I just compile it in the quarters. Yeah, here it is. Like based on the add and shift method, the shift operation generates the partial product while the add steps sums them up, and Wallen's tree relies on this partial product operation. And I need to use full adders and half adders in this method, like this. I assign all of them. Okay, that's it. That's for the Wallen's tree. And when I calculate the critical delay for this 5 times 5, oh no, 4 times 4 critical path delay, it's like I use 8 full adders, and each has 2 XORs which contains this numbers of gates, and I add them together and I got 136. Hey, that's it. Thank you for watching.